in this video, I'll be teaching you guys about transistors and how you can use transistors to make gates. Yes, gates aren't just a component, all right? Gates aren't just, oh, this is an AND gate automatically, right? AND gates are made of something, right? And they're made of transistors. So are OR gates and so are other gates. The thing is that there are different types of transistors. The one we're going to be talking about today is called the MOSFET. And what a MOSFET looks like inside of a circuit diagram is simply what I drew here, right? It's more angled. An example of another type of transistor, if I were to go a little bit off topic, is called a BJT. This is what a BJT would look like. But I'll explain the different parts of transistors. You might be wondering what this arrow stands for, what these types stand for, what is this guy right here, what is this extension outward. All right, these are all different parts of the MOSFET. And the reason why I'm talking about the MOSFET is just because it's the most widely used. But let's talk about the different types and let's talk about their functionalities first. So we have a P-type and we have an N-type. I'll cover the differences between those, but first thing I'm going to talk about is the P-type. So the P-type transistor, what does this do? Well, here's the thing about transistor. They actually act as switches. So this transistor right here will take in some input, 1 or 0. It's called logic 1 or 0, right? The binary logic 1 or 0. And I'll explain what those stand for. Let's move this up. What those stand for later on. But let's go ahead and explain that there's logic 1 and logic 0 for P-type. All right. So what does a logic 0 stand for? Logic 0 just stands for 0 volts, or very low voltage, matter of fact. So let's say, hypothetically, 0 volts, all right? Right here, a logic 0 stands for 0 volts. Easy to remember, right? Well, if you have 0 volts going into this input, into the transistor, then this transistor, this P-type transistor, will act as a closed switch. So if you don't know what switches are, I'll leave a video link down in the description for that. But what a switch looks like, something like this, right? And how they could be either open or closed, right? So this transistor actually can change the switches along the way without having to manually, flick the switch, right? For this, you would have to manually change the switch in the circuit diagrams you've been looking at. But a transistor can actually allow current to go through, back and forth. You can change as your circuit goes on. That's why they're so useful. So let's say this has a logic of 0. Well, for P-type MOSFET, a logic of 0, which stands for 0 volts into the input, gives you a closed switch, which allows current to go through. All right. So when you have a logic of 0 for a P-type MOSFET, it acts as a closed switch. Now, here's the thing about this. Let's say you have a logic of 1, right? Binary 1, right? This could be from the ranges of 3 to 5 volts, right? It just depends. Different transistors have different sensitivities, but you might see 3 to 5 volts usually. This just stands for a logic of 1. And the reason why it's 3 to 5 volts is because you can't get exactly 5 volts, right? That makes no sense. And anything below this would be treated as a logic of 0. So where does this voltage come from? Probably from some other source, or from you clicking a button on your keyboard or something like that, right? Or just the computer running. But that doesn't matter, right? We're talking about the circuit analysis of this. For 3 to 5 volts, you get a logic of 1. And when you have a P-type MOSFET, logic of 1 gives you an open switch, which means that current can't flow through, right? There's no path for the wire to go through, so current cannot flow through, so you get an open switch. All right, so 0 stands for closed for P-type, and 1, so logic 0 stands for a closed switch, 1 stands for an open switch, which means current can't go through. And another way to differentiate between a P-type and an N-type transistor is the arrow right here, right, this guy. If the arrow or the current symbol is at the top, then you have a P-type. If the arrow is at the bottom, you have an N-type. But let's write this down, okay? Let's write down the rules for this because it's easier to see when I write it down. So 0 stands for a closed switch, and 1 stands for an open switch. So when you have an open switch, no current can go through. When you have a closed switch, yes, current can go through. Yes, current. All right, keep that in mind. Now it's actually the exact opposite for your N-type. Let's make this smaller. So what I mean by the exact opposite, for an N-type, this guy acts as an open switch when you have a logic of 0 as the input. Right? Probably 0 volts, 3 volts. If your sensitivity was 3 volts to 5 volts for 1, anything below that would be logic of 0. And 1 would be a closed switch, which means that this N-type, when there is no voltage going through it, it acts as an open switch. All right. And when there is voltage going into the input right over here, then you would have a closed switch, which allows current to go through. So they're the polar opposites, all right? Just remember one of them, and you can remember the other. So P-type is closed by default. Remember that. So when there's no voltage going into the input, it's closed by default. That's how I remembered it, at least. It's closed by default, and then when you put in some power, boom, flicks open the switch. Now, just to answer some lingering questions that might be going on, you might be wondering what goes here and what goes here. What are the other ends of these transistors? Well, usually the top part will just, it will just either give you a voltage source. The circuit diagram might give you a voltage source up here, or it might just write down positive 5 volts. Right? It just might write down positive 5 volts up here, which stands for an input from some who knows where. It doesn't matter. Right? You're just looking at a small scale circuit for now. And this right here is simply the output. All right, you could think of it as, let's say you have a logic of 1 for this P-type gate. Well, when you have a logic of 1, you have an open circuit. So this 5 volts, this current produced by this 5 volts cannot flow through this since it acts like an open switch right now. So the current produced by this 5 volts, no, cannot go through. So the output would just be nothing, right? It'd be 0 volts. Not 0 volts, maybe 0 amps, 0 volts, doesn't matter. Output wouldn't have anything. And the same for the N-type, it might just have a positive 5 volts input here, right, from who knows where, and then the output would then again be, let's say this is a logic of 1 actually. The output would just be the voltage, or the current produced by the voltage. So 1 right here, let's say 1 means 3 volts to 5 volts. And when you have 1 for an N-type, you have a closed switch, which means this acts like a closed switch. Now keep in mind the drawings here I'm drawing aren't actually part of the circuit. I'm just drawing it to help you visualize what a switch would look like. But since it has a closed switch, oh, looky here. This 5 volts has a direct path to flow to the output, so that means there would be there's a current going through the output. But let's actually look at this in practice, how these transistors can actually form these AND gates or OR gates. What we have right here is a circuit with transistors. I'm already going to spoil this for you. This is a NAND gate. So yes, it is a NAND gate. A little spoiler, so you probably can already assume the outputs, but I'll explain how the outputs work here as well. How the inputs and outputs work. But we have 2 inputs, X and Y, just like the inputs in a NAND gate, correct? What I mean by the inputs at a NAND gate would be like this, X and Y here, correct? So we have 2 inputs, X and Y. And when you have 2 inputs, you have 4 possible combinations of these inputs. 4. Remember that? Okay, I'll leave a video link down in the description if you don't. But for gates. But these 4 possible combinations consist of 0, 0, 0, 1, 1, 0, and 1, 1. Let's take a look at the first case. 0, 0. Well, you have a p-types here, and the reason why I know it's p-types is because the arrow is at the top. If the arrow was at the bottom, this would be n-type. These are p-types. So, when you have a logic of 0 for both of these guys, you have closed switches for p-types. So, these 2 transistors act as closed switches, which allows current to flow through. So let's say these are both closed. That means this guy, the power from this guy, can flow all the way down on both sides, and then they connect at the end anyways. So when they connect at the end, what we have is this weird node here. Okay, what does this node stand for, and why is there a node here? Well, there's a node here because it's called the output node. If this output node detects anything between, let's say, hypothetically 3 volts to 5 volts, then this outputs a logic of 1. So in the case of an NAND gate, all right, let's say there was input 0, 0. When you input 0, 0 into a NAND gate, you get 1. So in this case, since this 5 volts was able to flow down and reach this output node, that means that you have, well, 5 volts at this node, correct? Well, since you have 5 volts at this node, that means the output is of logic 1. And since the output is of a logic 1 here, that means the output of this NAND gate would be 1 when you have 0, 0. Or this gate, this hypothetical gate. Nope, I'm not saying NAND gate yet. This hypothetical gate would have an output of 1. Let's do undo instead. And, of course, this guy would go all the way down as well, keep going down, hit the resistor, and then you wouldn't have an infinite current. You wouldn't burn up your circuit, all right? The resistors are pretty important because if you connect directly to ground, you will fry your circuit. It will literally set on fire. Let's see. And also, if your resistor isn't strong enough, that thing will burn up. Maybe you can try that in your lab. Okay, I'm not going to suggest it. But I did that. And I burned up a resistor and it smelled terrible. But you can try it out if you want. It's pretty fun. But this is in the case of logic 0, 0. All right. So logic 0, 0, we know that it outputs an output of 1. All right, let's look at logic 0, 1. Well, for 0, 1, 1 gives you an open switch. So this guy, current cannot flow through this guy right here. Nope. But current can flow through this guy still. So let's draw the direction of the current. Oh, goes all the way down, goes all the way down, goes all the way down, hits the node. Right. So there's a path for the current to hit the node, path of the voltage to reach this node. So the output is, again, 1. Right. And, of course, it'll just go all the way down, hit ground. But the output in the 0, 1 case is 1 as well. All right? How about for the next case, 1, 0? Let's take a look at 1, 0. Well, in this case, now this guy, it acts as an open switch. So the open switch, boom, no current can go through. But this guy, yes, current can still go through the right side. So we look at the path of the electricity, and it goes all the way down, hits the node. Therefore, this 5 volts is able to reach this node. Therefore, the output is 1 in this case. And, of course, it's going to go hit ground. The output would be 1 here. Now, let's take a look at the case of 1, 1. In the case of 1, 1, both of the switches, both of these transistors act as open switches. Therefore, no currents can flow through these. So, since no currents can flow through, it hits here, it stops. Therefore, this voltage cannot reach this node. So, there's like 0 volts here, basically. So the output would be a logic 0. And isn't this the exact output of a NAND gate? Yes, it is. Now, keep in mind, usually people don't use resistors for these gates. And I'll explain why. These resistors are big. They're significantly larger than transistors. You can get transistors. I think one transistor was like 1 nanometer or something like that. Some company made a transistor like 1 nanometer. Search it up, smallest transistor, which makes absolutely no sense because the width of an atom is like. Let me actually search this up right now. Give me a sec. All right, I searched it up. It's 2 nanometers. So if you don't know what nanometer is, 10 to the power of -9 meters. So basically 0.00000000001 meters. And here's why this is absolutely ridiculous. The width of an atom is from 0.1 to 0.5 nanometers. So this transistor that's 2 nanometers is made of 4 atoms? Right? Like how in the world do you do that? But the reason why this is, you don't really normally see resistors in the cases of gates is because these guys are big, right? You can get transistors way smaller. So what can you do? Well, instead of using a resistor, you can use, let's draw another node. you can use more transistors. Oh, you might be wondering, how in the world do you use more transistors? If you connect directly to ground, you'll be cooked. Well, you can actually use MOSFETs, and instead of these guys being P-type, you can actually set them to be N-type. So let's talk about that as well. So these are N-type, given the arrows at the bottom. And let's say they take the same inputs, X, Y. Right? So these inputs are the same, X and X, Y and Y. So you can imagine some wires connecting to both of these Y inputs and some two wires connecting to both of these X inputs. Let's take a look at logic 0, 0 for example, and I'll cover more gates and circuits later on. But take a look at logic 0, 0. Well, at logic 0, 0, we have, let's write down N-type. We know that we can get a voltage here, right? All the way down here, we know we can get a voltage. So N-type, 0 is open, 1 is closed. It's the exact opposite. So we know that we can get a voltage at this node right here with logic 0, 0, because the output is 1, right? But let's take a look at the inputs, 0, 0, for these two gates here, down here, these N-types. Well, remember, an N-type gate has an open switch. So when the logic is 0 going into it. So remember, our logics are 0 and 0 for X, Y. Therefore, the inputs logics are 0, 0 for X, Y down on these two transistors. Well, if you have 0, 0 as the inputs for these N-type transistors, then you have open switches. If you have open switches, that means current can't go here. Let's draw this. Current goes down here, boom, hits this. Current goes here, hits this node, and current actually gets caught. Boom, cut. It gets cut because these switches act as open switches. When you have logic 0, these N-type gates act as open switches. Therefore, you can't reach ground. This current can't reach ground. So if the current were to reach ground, again, your circuit, your wire would melt, basically. It would heat up way too much. So this is why this is important, right? You don't use resistors, you use transistors usually in real life. You use transistors because they can actually, they're smaller, and they can actually prevent this current from hitting ground by just setting these transistors as the opposite as the transistors up above. So what I mean by opposite is just P-type to N-type. Opposites, right? And if I were to look at another example of, let's say, logic 1, 1, right? I'll work this through with you guys in case you don't have a mind of your own. Logic 1, 1. So 1, 1, although these two switches, now, since they're N-type, they act as closed switches, which allows for a path of current to flow through. All right? These two switches right here, or transistors, act as closed switches, so current can flow through. But how about these two up here? Well, these two are P-type. And when you have a logic of 1 for P-type, they act as open switches. So this current right here cannot even reach below these two transistors, because these transistors act as closed switches, so current can't even go through them. So it doesn't matter if these two are open, there's no current above. Therefore, there's no current connecting directly to ground with no resistance. Therefore, your circuit will not burn up. All right, you can try this with multiple other things, but this is why this is useful. You can actually pack these gates even smaller, so you can get more transistors in a spot to make your computer faster, of course. So yes, the smaller the circuit, the more transistors you can pack into it, which means the faster your computer can be, right? That's why they don't use resistors. But let's talk about another circuit. That's enough on this example. New example, let's take a look at this gate, or this circuit. Looks a little more simple. There's only one input X. I guess you can already take a guess what this circuit is, but let's look at this. P-type, N-type, right? So this guy right here, let's just mark it down. Maybe it'll help you a little bit. But this is a P-type and this is N-type. So since there's only one input, we only have two possible combinations of inputs, 0 and 1. So let's take a look at the case of 0. Let's put a logic 0 here, logic 0 here. When you have a logic 0, for a p-type circuit? You take a guess. You try to remember this. Don't go back in the video. Okay, I'll give you the answer now. When you have 0 for a logic of p, you have a closed switch. So this guy allows for current to flow through, right? It acts as a closed switch. This transistor now acts as a closed switch. So current can flow through. And how about this for an n-type? Okay, let's write down close here, actually. Closed. Well, for an n-type, it's the opposite, right? So 0 for an n-type stands for an open switch. The opposite of the p-type. So we have an open switch here. No current can go through this guy. So we have this 5 volts up here. Let's look at the path of this. Well, since this acts as a closed switch, oh yes, current can go through, and it hits this node. Therefore, this node has voltage as well. All right, this 5 volts can go all the way through and hit this node. And it goes out. Well, since you actually have 325 volts at this node, what does this stand for? It stands for a logic of 1. So when you have 0 as your input, your output is 1. And keep in mind, the reason why this transistor down here is important is because, boom, this guy acts as an open switch when you have a logic of 0. And therefore, you cannot, oh, excuse me, oh my god, that's so rude. This current cannot reach ground. So that's important. Your current must not reach ground. But let's erase everything. Erase. And this is a logic of 1. You can already take a guess what the next logic is. It's 0, right? So this is a NOT gate in transistor form. But I'll work through the logic, of course. 1 here as the input, 1 and 1. A p-type gate acts as a an open switch. An open switch with logic of p. Logic of 1. What am I saying? So this guy is an open switch. No current. It's open. No current can flow through this. All right. Since no current can flow through this guy, this 5 volts, boom, gets blocked off. Therefore, this voltage at this node is 0 to 3 volts, right? Somewhere around that range. Therefore, the output of this would be a logic of 0. And although this is a closed switch which allows current to flow through this transistor, it doesn't matter. There's no current even going through it since this guy was blocked off from the very beginning. So the current doesn't connect directly to ground. And I'll cover one more. I think I'll cover I'll talk about the AND gate. No. Let's talk about the AND gate. Yeah, that's a good idea. But I encourage you to try to make these circuits yourself. It's a good exercise. I encourage you to try to make them yourself. All right. If you try to make them yourself, you should be able to. I think you guys could do an OR gate yourself. All right. Just draw it out. Have some fun. Try it. If you don't care, if you want to just pass your class, I don't know. You're not reaching for the stars or anything, but you're gonna get your diploma, so that's fine as well. Yep, this guy. Big circuits. It's actually quite easy to understand. But let's take a look at the possible inputs. We have X, Y, and XY. Here's the thing about this. I actually covered this at the beginning of the video, but this is a NAND gate. This is a NAND gate. And I also covered this previously. This is a NOT gate. So guess what happens? You combine a NAND gate and a NOT gate, you get an AND gate, right? That's how you get AND gates. So let's actually go through all the possible inputs, okay? Let's go to 0, 0, 0, 0. Right, this is 0, 0. So we know these are p-types because the arrow is at the top, and we know these are n-types. This is n-type and this is p-type. It's pretty nice to write it down at the beginning. But remember, 0, 0. Right. This the transistors act as closed switches, so current can flow through both sides. And it reaches the output gate. But since 0, 0 for n-type gates acts as open switches, current can't go and hit ground directly. That's a good thing, by the way. Which means that you get a logic of 1 for 0, 0. Alright, let's take a look at other logics. Let's say, you know what, let's look at 1, 0 next, because I already erased that, might as well just skip a little part. But 1, 0, this acts as a closed switch, and this acts as an open switch now. That's the only difference. So, since now this is, I reversed it. This acts as an open switch, this acts as a closed switch, sorry. So this right here allows current to flow through, but this side, no current can flow through. So we have current hits this output. The output Z is now 1. 1, right? Sorry, 1 for this, since this is 1, 0. And we already know that this is a NAND gate. I'll just fill out the rest. All right, so we have 0, 1, right, is equal to 1, and 1, 1 is equal to 0. So for this NAND gate, if I were to review for a little bit, 1, 1, these are P-type gates. When you have 1, these act as open switches, therefore no current can flow through. So current gets cut off here, therefore there's no voltage at this output gate, or this output node. Alright, here's the thing about these output. This output goes directly into another circuit. And this other circuit these outputs directly go into other transistors and other circuits. So, let's look at the first case. 1 is the output for this NAND gate. So let's look at, so now 1 is the input for this gate right here. Or this potential gate. So you have 1, 1 for these, 1, 1 for these transistors. Alright, so when you have 1 for P-type gate, what do you get? Well, when you have 1, P-type gates are open. So since it's open, this voltage and no current can reach this node right here. Therefore, this node has a voltage of 0 volts. And remember, 0 volts as an output is treated as a logic of 0. And that's the same for all the other cases of 1 as well. All right, let's take a look at the output 0 for Z, but also the input 0 for this circuit. So 0, 0. Remember, for P-type gates, 0 act as closed switches, therefore current can flow through. And for N-types, it acts as an open switch, therefore no current can flow through. So we have the current going down here, hitting this node, but the current can't go past this transistor, so it doesn't reach ground. Good thing. All right, now this current goes all the way down, hits this node, and this voltage reaches this node as well. Well, since the voltage reached the node, we have a voltage of between 3 to 5 volts for the output. And 3 to 5 volts for the output stands for an output of logic 1. So, right here are inputs at the beginning, 0, 0, 0, 1, 1, 0, and 1, 1. And right here are outputs, 0, 0, 0, 1. Right? These are the exact outputs of what you would expect from an AND gate. So all we did to make an AND gate was to connect a NAND gate and a NOT gate. And this is how real computers work. Right? They just have transistors, and they make a bunch of gates to do arithmetic as well. Right? CPUs do arithmetic. I think the ALU, the CPU, does arithmetic. I'm not certain. I'm not that part of computer engineering. I'm literally just a freshman. Well, I'm going into sophomore year, but that's irrelevant. As always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. And thanks for sticking through this long process.